there any questions before we get started? Well, let's go ahead and review just a little bit what we said. In this chapter, we started off talking about basic substances, mixtures. We said that mixtures come in two forms: heterogeneous, which are the classic things we think of for mixtures, where you have lots and lots of little chunks of rocks and stuff like that. And homogeneous mixtures. Homogeneous mixtures, things like air, salt water solutions, where it's not obvious that the things are mixed together, and you cannot simply reach in and pick them out. Talked about elements and compounds. Element is the simplest form of matter. We talked about the elements on the periodic table, whatever. We said that if you take two or more elements and you combine them in a specific and constant pattern, that you will get a compound. We'll see in chapter 3 that compounds come in two flavors. One is called molecular. Methane, that's natural gas, is an example of a molecular compound, and we can refer to something like this truthfully as a molecule. The other type is an ionic compound. They differ in the fact that a molecule like this has a defined geometry. Excuse me. Sorry. I always have to look, I'm sorry. Like I said, I've got a bunch of kids, and I'm sure you guys can understand. So, but that wasn't one of them. All right, so anyway, an ionic compound, you have a specific ratio, but you don't have a spatial determination like you do in a molecule. We'll understand that when we do chapter 3. We talked about density. Density is simply mass per unit volume. What you need to do is to take the mass. Classically, the mass is expressed in something like grams, the volume in cubic centimeters. Conversions that you need to remember. Cubic centimeter is the same as a milliliter. They're exactly the same volume. 1 liter is 1,000 cubic centimeters. And then if we take 1/1000th of that liter, we get the milliliter. You can express density in virtually any units, however, as long as you have mass in the numerator and a volume unit in the denominator. All right, we looked at some problems. This was the last problem that we looked at. This is an old test question. And let's just go over it again to get a running start at looking at the metric interconversion tutorial. Is all of this in your way a bit?
That's better, yeah.
We had 62.58 cubic centimeters of something with a density of 0.001 kilograms per milliliter. And we're simply trying to pick out the appropriate mass in milligrams of this sample. All right. When we approached this was to simply do our formula. We know that density is mass per unit volume. If we substitute in our things here, we have a density, we have a volume. Now remember, milliliters and cubic centimeters are the same thing. So we can just take this, rearrange it, solve it for mass, and we get our mass now in terms of kilograms. So that's the easy part. Very simple little mathematical exercise. Unfortunately, we want this thing expressed in terms of milligrams, not kilograms. Now this is a place where we use our ratios and our given. lot of these things you'll be able to do in your head, okay? The very simple ones, like kilo to milli, et cetera, just like this problem. Some of them get a little more complicated, but this one is fairly straightforward. If we were to solve this using our ratio method, we would start off with our given. That's what we just calculated as our mass in terms of kilograms. We have to plug in a ratio of some sort. The ratio is going to be between grams and kilograms. And again, you can use any of the ratios you want to write, as long as, number one has to be right, but number two, kilograms has to be in our denominator. Kilograms in the denominator will cancel. That means our given now has units of grams. So our second ratio has to be set up with grams in the denominator. We are converting here from milligrams to grams. We know that there are 1,000 milligrams in every gram. Our grams are going to cancel. And when they do, we're going to get an answer here now in terms of milligrams. We get 6.8838 times 10 to the fourth milligrams. Now, if you have trouble with these exponent deals, please practice the exponent tutorial. It's not difficult. Here we have 10 to the third, 10 to the third. They're going to add, so that's 10 to the sixth. This is 10 to the minus 2. Going to add it, and that makes it 10 to the fourth. Now we look at these and we try to pick out our correct answer. This is the same as this, obviously, but the real problem is that our problem here is stated with only two significant figures. Because we only have two significant figures, we have to round this to two significant figures, and that is the proper answer. So it's a multi-step problem. First thing we had to do was to go through and actually solve the very simple math using the equation. Then we had to do the method of conversion. Because it's a multi-step problem, it's a little more difficult. You won't see a lot of them on exams, but you will see, and they will be featured in the quizzes. Remember, we're going to take our first online quiz just before our first hour exam. So that's just after we finish chapter 3. The online quiz will feature questions based on these tutorials. Let's just run through the density tutorials very quickly. They start off with density 1. Now density 1 is really, really simple. We're given a table and we are asked to fill in the missing spot. On Blackboard, it would be the same thing. You'll get two values and you have to enter something else. Remember, no units, just numbers. So we look at this. We simply have to calculate a density, we are given a mass, and we are given a volume. Our density is going to be mass divided by volume. If we plug this in, we get 24.8 grams, 18 cubic centimeters, and our density is 1.37. Now on the tutorials, you don't have to be compulsive about significant figures. That's because getting JavaScript to calculate and recognize significant figures is difficult. Some of the tutorials work, some of them don't. Don't be compulsive. In fact, this is a secret of the way I set up the correct or not correct here actually gives you slop of about 5% on the answer. So if I entered 1.36, it would still be right. Same thing with Blackboard. On Blackboard, I give you like 0.02 leeway just in case there's a simple rounding error or something. This is another version of density 1. Here we are given a mass, we are given a density. We have to calculate the volume. Why don't you do that quickly while I pace? We're going to take our equation, density is mass divided by volume. We're going to rearrange it so we're solving for volume. Volume is going to be mass divided by our density. Simply plug in the two values. Our calculation should be about 51.5. Well, let's do another. Here we're given a volume and a density, need to calculate the mass. Do it the same way. Start off with density as mass divided by volume, solve for mass, and plug in. Mass is going to be our density multiplied by our volume here. Simply plug the numbers in. Here's our density, here's our mass. We do our calculation, and it should be about 54.7. So, density 1 is the most straightforward. Oh, here's one more density 1. I didn't think I had one more. Same sort of thing. We're solving for mass, density times volume, plug the guys in, 25.8 this time. The neat thing about this, of course, is that because these are all algorithmic, every time you click new problem, you get a new set of numbers to work with. So you can do it until you really get it down. All right, density 2. Density 2 is pretty much the same as density 1, except for two things. First of all, instead of a table, it's a word problem. Now, people traditionally hate word problems, but they're really no different than our table. Secondly, we're going to be given mixed units here. So in this one, we're looking for a volume in cubic centimeters. We are given kilograms of a substance, and our density is 9591 milligrams per cubic centimeter. So we have to do both metric conversion as well as our basic calculation. Well, as we look at these, there are going to be a couple conversions we have to deal with. Our mass unit starts off as kilogram. We need to get it down to milligram. So we need to plug in, we're going to use our algorithm, of course, and we're going to plug in two ratios. One is going to be kilograms to gram. That's 1,000 grams per kilogram. And our other one is going to be grams to milligram, 1,000 milligrams in a gram. So our logic is what we're doing. So our logic is going to be to take and set up two ratios. Our mass here is 0.00169 kilogram. We're going to convert that into grams, knowing that there are 1,000 grams in every kilogram. The second thing, our density here is given in terms of milligrams. We know that there are 1,000 milligrams in every gram. So we can simply take this number, move our decimal over, and we have 9.5 grams per cubic centimeter. Now we just want to take those numbers, plug it into our standard equation for density. When we do that, we get 1.76 as our volume in cubic centimeters. Now I hope you noticed on Blackboard, and I hope you've noticed on these guys, that after you do a calculation like this, if you get it wrong, or if you get it right for that matter, and you just want to know exactly how to do it, make sure you're doing it right, you can click on Show Answer, and somewhere magically down here, the entire calculation will appear. So on Blackboard, after you finish the quiz, if you click OK a couple times, you will get your results. And under, quote, feedback, for each of the problems on Blackboard that are based on tutorial, you will have feedback that has the complete solution. So it's a nice way to review even if you miss one.
I have a question. When you convert the kilos for the grams, why here is 686, not 1690? The kilos to grams.
Kilos to grams. Oh, here. Oh,
You know,
well,
I mean,
let's see, 690. Okay, you're right.
I mean,
Because, again, this is a rounding problem. This is actually from the solution
okay,
at
so
the end.
okay, so if you will write.
No, this should be
1.
1.69.
Okay, 0. That's okay. I just need to
Yeah.
know because then I know if I'm right or wrong.
Nope, it's mine. All right, here, we're looking for a density. We're looking for grams per liter. We have cubic centimeters for our volume and kilograms for our mass. The two conversions we need to do are from kilograms to grams. And hopefully we start to be able to do these things in our head, right?
This is
It's
the
a factor of
worst.
1,000, isn't it? And finally, we are given cubic centimeters. Well, that's the same thing as a milliliter, right? And there are 1,000 milliliters in every liter. So we could simply convert this to liters by dividing it by 1,000. Move our decimal over, and these are our numbers. Finally, we do our calculation using our basic formula here. We're looking for density, so it's just this way. Take our mass, divide it by our volume in liters, and it should be about 8340. Now, you know, these involve really two things. It's a simple conversion, or it's a set of conversions first, followed by a very simple calculation. It's kind of like real life. If you were given something in one set of units and you had to use it in another, you would do both the conversion and the calculation. The other tutorial that's there for this section is called metric interconversions. Here, all you do is the conversion part. So you don't have to worry about doing the calculation part. Just check your ability to set up ratios. This one also features the ability to read e-notation. So if you have a number with lots of decimal places in front or back, you can replace that with scientific notation. For example, if it was 1.2 times 10 to the minus 3, you could write that number in your answer slot here as 1.2 e minus 3. And interestingly enough, when Blackboard is working properly, which it does sometimes, it will also read e-notation for these same types of answers. Now, they continually update Blackboard. That means that I continually have to go in and check to make sure it still does it. Because twice now, they have somehow deleted that, and we had to have them recompile and reinsert it. But this should work on Blackboard. I haven't checked yet, but it should. All right, we have a density in terms of milligrams per liter. And we want to simply convert this to grams per milliliter. So we need to do two conversions here, don't we? We have to go from milligram to gram. Well, we can do that. There are 1,000 milligrams in a gram, right? And the other thing we have to do is from liter to milliliter. Well, there's 1,000 milliliters in a liter. So both of these are just simple fractions with units of 1,000. Our first one, from grams to milligrams. This is a ratio that we could write. 10 to the minus 3 grams is the same as 1 milligram. We could also say, for liters to milliliters, that 1 liter is the same as 1,000 milliliters. Finally, here I've taken our given, which is our density. Here's my first ratio. Here I have milligrams and milligrams, and those two will cancel. In my given, I also have liter in the denominator. That means I need a ratio with liter in the numerator. So this liter and this liter will cancel. And we simply do our calculation. This turns out to be 1.1, exactly the same number we started with. We're going from a factor of 10 to the 6th to a factor of 1. Any questions? Let's do one more of the metric interconversions. Here we have a density that is given in terms of grams per milliliter. You want to convert that into a density, of kilograms per liter. The ratios we need are going to be grams to kilograms and milliliters to liters. These are both factors of 1,000. We all know them. Go ahead and just write your two ratios. Since we have grams per milliliter, our first ratio must have grams in the denominator, and our second one must have milliliters in the numerator. Our first ratio, something like 1 kilogram is 1,000 grams. That works because we have grams in our denominator. Our second ratio, we can do 1,000 mils in 1 liter. That works because milliliters in the numerator and it's in the denominator here. All we have to do is line up these ratios and multiply it by our given. Here's our given. Grams are going to cancel. Milliliters are going to cancel. And we are left with 3.45, exactly the same as we started with, as our answer. Any questions? All right, let's just wind up this with a couple more examples of test questions. Once again, I don't like exams to be a surprise. Before we take our first exam, you will have 2 practice exams. One will be a blackboard exam, and it will have the same material. A lot of it will be in tutorial format, but it'll be mixed in with multiple choice questions. You can practice that, take it as many times as you want. Make sure you understand the material and whatever. It's not graded. You will get a grade, but it does not count, doesn't show up at all. The other exam you'll get is going to look exactly like the exam that you will take in class. Now, when I say look like it, I mean it'll look like it. Okay, it'll have the same style of questions, the same boxes, the same everything. The idea for that is to help you with test anxiety. Nothing is worse than coming in and picking something up and having it look foreign. I have no idea, I've never seen this stuff before in my life, sort of feeling. Here, you come in, you pick it up, you say, hey, it looks just like the other one. Now all the questions are different. And all the answers are too, but it looks just the same. And that's a real comforting thing for students. It really is, trust me. Okay, here's one of the test questions on this area. We want a mass in milligrams. We have 9.91 cubic centimeter as our volume, and we have a density. What I'm going to do here is simply take my given, which is our mass in milligrams. I'm going to use my density here as a ratio. And I'm going to make sure that cubic centimeters, that is the units of given, are in my denominator. So we do this very simple calculation. This is very much like the tutorial density 1. All we're going to do is take our 9.91, multiply it by this, divided by 1,000. We could also do it this way, using our formula, plugging in, solving for mass. Keep solving. There it goes. 32,187 grams. All right, so that's the answer. What is the proper answer on the exam? Which of these is going to be equal to 32.187 grams? What you need to do is to look at significant figures, don't you? First of all, you know, if you look at significant figures first, you can just dump a whole bunch of answers, can't you? And narrow it down. So we have 3 significant figures here, we have 4 here. Our answer is going to be 3 significant figures. Yeah?
How did it just randomly change from grams per liter to grams per centimeters cubed?
Oh, I did 2 things in this transition here. Remember, this is the same as 1,000 milliliters, isn't it? Which is the same as 1,000 cubic centimeters. So in one fell swoop, I divided this by 1,000, so 3,200 down to 32. And I just substituted cubic centimeters for milliliters. 2 things at once, sorry. All right, so we're looking at 3 significant figures. Well, this has 5, that has 2, that has 4, and of course the dreaded none of the above. If we converted this into milligrams, it would be 32,000 of them. To 3 significant figures, it would be this guy. So this is an example where significant figures can be your friend. Following up on the question back there, the advantage of using the given and the ratio is that you didn't have to do this little bit of thinking here, did you? You just set up the ratio, it will do it automatically. Let's do one more. Here's our density of mercury. What's the volume for 990 grams? Now we could do this using our ratio, but just to point out once again the unit deal, let's go ahead and solve it with the formula. So we're going to say volume is mass divided by density. Okay? Well, that's simple. We have a density, we have a mass. Plug in our mass. Here is our density. Now when we see something like this, remember, please, we have cubic centimeters in the denominator of the denominator. Our grams are going to cancel, but because our cubic centimeters are buried all the way down there, 1 over cubic centimeter is equal to cubic centimeter. So this guy's going to come all the way up top. I hope. There it comes. Now we do our simple calculation, 990 divided by 13. And we get 73.084 cubic centimeters. That's this guy, right? However, how many significant figures do we have? Let significant figures be your friend. We have 2. So, this isn't the answer, is it? Is this the answer? This has 2, this has 2. If we round 73.048 cubic centimeters to 2 significant figures, we get 73.
They the same because 10 to the -1.
And we could write 73 as 7.3 times 10 to the first. So, both A and C are correct. Okay, let's move on. Stop talking about math for a little bit, and let's go back to simple chemistry. We talked about physical properties. We talked about properties in general. Remember, I said we were going to deal with chemical and physical. Physical tells us something about the characteristics, physical state. Density is a physical property. And we all know about density now. A chemical property tells us how a material is going to act when it's combined with another chemical substance. If a substance undergoes a physical change, it's still the same substance, still the same molecule, still the same. It just, something has changed. It has melted. It has boiled. But it's still the same. If something undergoes a chemical change, when it combines with another substance, then we have a totally new substance being formed. So a chemical change is going to give us a totally new substance. Let's look at an example. This is the little vial that we looked at some time ago, filled with bromine. Here the bromine's all melted. Remember, it's a liquid. Has a high vapor pressure. It's very brown. So the gas above it is very brown. This is a lump of aluminum. Both of these are elements. Aluminum's a metal. I've shown it here just as a cluster of aluminum atoms. Bromine's also an element. It's a halogen. Remember we said that the halogens, fluorine, chlorine, bromine, and iodine, were going to be examples of diatomic elements. That means that every bromine exists as Br2. It's important to remember those because in the future, when I say bromine, I'm not talking about Br, I'm talking about Br2. Okay? All right, well, if you take aluminum and bromine, 2 elements, they all have their same set of chemical and physical properties. What I'm going to do is take this beaker. This has some bromine in the bottom. You'll see it's full of bromine vapor, and this is a little pile of aluminum shavings. Very carefully pick up the aluminum. Pour it into the bromine, just a little bit. It sits there for just a minute. And as it does, suddenly you get lots of heat. You get lots and lots of bromine vapor. Hold your breath. Very toxic stuff. And when finally the reaction's all done, if you look at your vessel, all along the walls and actually around the rim, we have a white crystalline solid. The white crystalline solid is totally different than the bromine we started with or the aluminum. This is aluminum bromide. It's a totally new chemical substance. This is a classic example of a chemical change. Now soon we're going to talk about chemical reactions. That's the fun part of chemistry. When we do a chemical reaction, we're going to describe it somewhat like this. We're going to have a set of reactants, and we're going to go to a product. The arrow here has the same properties as an equal sign. Now what that means is, in terms of chemistry, that you must have the same numbers and types of atoms on this side as you do on this side. Interestingly, you also must have exactly the same mass on this side that you do on this side. But we'll talk about all those as we get into reactions. Just to differentiate, once again, chemical changes and physical changes. This is a set of icicles. And pretend this is Sunday. Sun was beating them on them, and they were dripping. We have water vapor in the air, water in the gas phase. This is liquid water dripping off. And of course, this is ice, which is solid water. They all look different, but they're all still water. Changing from gas to solid to liquid is a simple physical change. We can also take water, which is 2 hydrogens and 1 oxygen, and we can break it down into oxygen gas and hydrogen gas. This is the process of electrolysis. If we put water into a vessel like this, put electricity through the both sides, interestingly enough, hydrogen will bubble up one side, oxygen will bubble up the other. There are 2 hydrogens for every oxygen, so you'll notice there's a bigger volume here of hydrogen than oxygen. Also notice oxygen and hydrogen both are more examples of diatomic elements. Again, when I say oxygen, I mean O2. And when I say hydrogen, I will mean H2. Simple physical change, simple chemical change. Any questions? All right, very simple, silly answer or question. Just quickly run down these things and decide for yourself. Is this chemical? Is it physical? Frost forms as the temperature drops. All we're doing when we make frost is what? Making water in the gas phase and making it into water in the solid phase. This is a simple classical physical change. Cornstalk grows. Hopefully this happens every spring. Well, This is actually a set of very, very complicated chemical changes because the corn undergoes germination. We have lots and lots of biochemistry that happens as the DNA in the seed begins to replicate, pull in nutrients from the soil, blah, blah, blah. Very complex set of chemical changes. This guy's a much more direct thing. We light a match. When we light the match, we get ash at the end. And of course, we get a good big proof of gases as the match head burns and as the match itself burns. This is another classical chemical change. All right, the next one, you sweat. Therefore, you are. But when you dry off, what happens? It goes from water in the liquid phase to water in the gas phase. Still water, still physical. And the last one here, silver tarnishes in air. Nobody uses silver anymore. One of the reasons is it tarnishes in air. And that's a real bummer because you have to polish it all the time. What's actually happening here is that the air will contain a little bit of dihydrogen monosulfide, also just called hydrogen sulfide. And this undergoes a chemical reaction with silver to give a silver sulfide, which is black. So this is a chemical change. Now, you know what? Polishing silver was a real drag. It really was. But using silver as your dinnerware or whatever was actually a very good thing. Because it turns out that if you have, say, a cup or a spoon made of pure silver, that as you eat and drink from this utensil, a little bit of the silver is going to dissolve. And so your body is constantly flushed with these silver ions. And you might think that that's a bad thing. But it turns out that silver is very good at killing bacteria. It's very antibacterial. So if you use silver cup and you happen to be living in medieval times, and the water was polluted as all get out, you were much less likely to die. Now, who used silver cups in the medieval times? Nobility did, of course, right? Because nobody else could afford it. But it turns out that lead also is antibacterial. So, the lower populations would use lead-based utensils and cups. Worked the same way. It killed the bacteria, that was good. But unfortunately, unlike silver, lead is a neurotoxin and makes you really stupid. So you wound up with a really stupid peasant population and a set of stupid nobility that, well, they just worked. All right. Let's look at what we said about chemical reactions. Chemical reactions, once again, are going to describe a chemical change. We're going to have reactants on one side, an arrow, and we're going to have products on the other. An example of a chemical reaction is something like this. K, we all know now, is potassium. Potassium will react with water. Water has 2 hydrogens for every oxygen. That's H2O. When they react, this will form potassium hydroxide. That's KOH. We'll talk about that in chapter 3, I think. And we'll also form hydrogen gas, which we all know now is H2. This is a chemical equation. Reactants and products. Now, point out a couple things here. We have an S, an L, an AQ, and a G. S stands for solid. That means we're starting here with solid potassium. Water is a liquid. That's our L. KOH, AQ, that stands for aqueous solution. So it's potassium hydroxide is dissolved in the water. And finally, G is for gas. Hydrogen is going to bubble off as a gas. So that's one thing. That's what all the little letters are. Lots of equations that you'll see will have little letters. Some of them won't. The letters are there as a guide to you when they're important. As you get deeper into chemistry, letters will disappear because they're a bother. The other thing I want to point out are these numbers. Those numbers are called coefficients. What the numbers tell us is that it takes 2 potassiums, and that will react with 2 waters. When it does, we will get 2 potassium hydroxides and 1, we don't show 1, hydrogen. Now remember what I said about this being an equal sign. I said you must have the same numbers and types on both sides, right? So on this side we have 2 potassiums, right? Here we have 2 potassiums. We have 4 hydrogens. Over here we have 1, 2, 3, 4 hydrogens. Here we have 2 oxygens. Here we have 2 oxygens. So we have the same numbers and types of atoms on both sides. We'll see late in the lecture, Lavoisier also pointed out to us years ago that we have the same mass on both sides as well. All right, well, this is a chemical change. If you actually do this, if you take potassium and dump it into water, they will react. They'll react violently. If you have a big chunk of potassium, it will explode, actually. We're going to do this in a very controlled way. When we dump in our potassium, this reaction is going to generate heat. When it does, it's actually going to melt the potassium. So it's going to go from a lump to a little melted lump. And the hydrogen that's formed is going to get so hot that this is in turn going to react with oxygen and it's going to burn. Kind of a cute thing to look at, a lot of fun to do. Can't do this in lab, they won't let us, but you can watch it anyway. Potassium is stored in mineral oil. Soon as it hits, you'll see it goes into a little ball, hydrogen goes off, and it burns. Clearly, if you had a big chunk of it, that's so much fun, let's do it again. Clearly, if you had a big chunk of it, this would happen very fast, and you would get lots of hydrogen, lots of heat, and a big explosion. The process, once again, solid potassium plus water, potassium hydroxide, and hydrogen gas. Any questions? I said the hydrogen that's formed react with oxygen to give water. That's why it seemed to be burning. Once again, hydrogen and oxygen are both diatomic. We have 4 hydrogens here. We have 4 hydrogens here. 2 oxygens, 2 oxygens. So this equation is balanced. Now this is also something that's very fun to do in lab. Again, you really can't, but this brave person is going to do it for us. You'll see this is a lighter on the end of a stick. Hopefully you'll see why. Very carefully. That was so much fun. Let's do that one again too. On a long stick, balloon is filled with hydrogen. Back in the old days, we used to be able to do things like this in lecture, but you know, it was life and limb for the people in the first rows, but that's what you get for sitting up front. Any questions? Another simple example of a chemical change. All right, go ahead, look at these guys, determine if this is chemical or physical. Well, if we take a gold bar and we hammer it out into a sheet of gold leaf, we still have gold. It's just really thin. Classic example of a physical change. Gold is the element that is the most malleable. What this means is you can take a little bit of gold and you can hammer it out into a phenomenal surface area. You can actually hammer gold so it's just 2 or 3 atoms thick. Gold leaf. Sometimes you'll see, like churches or whatever, where the entire dome is literally covered in gold. And you think, wow, that's a lot of gold. Well, it probably isn't. Probably a lump this big. But you can hammer gold leaf so thin that you can cover just a huge surface, which is a very small amount of material. Beaker of water is heated to boiling. Well, by gosh, it's boiling, but it's still just water. And finally, if we do barbecue, start off with carbon. Heat it up in oxygen, we get carbon dioxide, we get heat, all of those things. Classic example of a chemical change. Now there won't be a lot of questions like this on the exam because these are real simple. But it's just a very basic concept. Make sure you get it. All right, remember I told you that Lavoisier told us something about chemical reactions and mass. This is called the principle of the conservation of mass. Now, these little videos that we showed showed chemical reactions happening. And you'll note that as these happened, in general, there was like flame and fire and stuff like that. Because of that, the thinking at the time was that you were losing mass as these things happen. That all this heat and light that goes off is somehow missing mass when you wind up. Lavoisier was the first person to actually demonstrate that that's not true. That when you do a chemical reaction, the mass of the reactants will equal the mass of the products. That's the principle of the conservation of mass. Now he used something that looks like this to demonstrate it. Here's a little retort. You could heat the thing up. This was a vacuum chamber. You could collect stuff here. etc. What he did was, he started with mercury. Remember the fun element. They played with it too. And if you heat up mercury in the presence of oxygen, you get this red solid called mercury 2 oxide. Well, what he did was, he very carefully weighed out the mercury he started with. He weighed out exactly how much oxygen was consumed and how much material was formed as the mercury 2 oxide. And what he demonstrated was the mass of these guys equal the mass of this. Not only that, but if you started here with mercury 2 oxide and you heated this up, you could reform oxygen and mercury, and that this cycle had the same masses on both sides. So kind of a really neat thing. For his day, he was clearly quite a thinker. Looks like a thinker, doesn't he? Unfortunately, this was the time of the French Revolution, and the people that were revolting in France did not like neither scientists nor chemists, and so they chopped his head off. And the judge, this is the quote from the judge at the trial, the Republic needs neither chemists nor scientists. It was a shame, because he was actually fairly polite for his day. Maybe that's what's wrong with France even today. All right, let's look at a handful of exam questions dealing with Chapter 2. As always, these are real, simple exam questions. What's a physical change? Lighting a match, sugar and tea, melting aspirin. Clearly, if we light a match, we're going from match to something else. So that's not, is it? Sugar and tea. It's still sugar. Melting of aspirin. Most people look at this and say, well, gee, you can't melt aspirin, it's a pill. Well, actually, you can melt aspirin. It's a chemical compound, acetyl salicylic acid, and yes, it does melt. So B and C are both physical changes. What are chemical properties of carbon? It's a solid at room temperature. It's insoluble in water. Soluble in carbon tetrachloride. Molecular compound, we'll learn that in Chapter 3. Reacts with oxygen. Crystallizes to form diamonds. We're looking for chemical. It's a solid. That's a state. That's physical, right? Insoluble in water. Soluble in carbon tet. But it's still carbon, isn't it? Nothing happens when it dissolves, just like sugar and tea. Reacts with oxygen. Yes, that's going to be a chemical reaction. How about diamonds? Diamonds are still carbon. You can burn a diamond just like you can burn charcoal. Don't try it. D is the only example of a chemical change. Which of the following is correct? Compounds cannot be decomposed into elements. Elements and compounds are pure substances. Elements but not compounds are pure. A and C, or all of the above. Well, you can kind of rule out all of the above right away, can't you? Because these are opposite statements. Can we take compounds and convert them back into elements? Yeah, sure. I mean, a compound is just two or more elements stuck together. We can stick them together, by gosh, we can rip them apart. These guys, elements and compounds are pure substances. Yeah, that sounds good. Elements but not compounds are pure substances. This is the only one that is correct. We actually saw Lavoisier take mercury 2 oxide and convert it back into mercury and oxygen. So these can be decomposed. All right, if we have 50 aluminum sulfates, how many sulfurs do we have? Now let me point out two things here. Formula unit. Everybody is going to want to call this a molecule, but technically it's not. We'll learn that in chapter 3. So we have to call it a formula unit. What that simply means is one of these guys. So look at this and answer the question. If we had 50 of these, how many aluminums would we have? Well, there are 2 in every one, right? So therefore, there would be 100. 100 aluminums. Now, what does this thing in parentheses mean? That means for every 2 aluminums, we have 3 of these guys. So, in every one of these units, we have 3 sulfurs and 12 oxygens in every one. Therefore, if we have 50 of them, and there are 3 in every one, we have 150. As we work our way through polyatomic ions in chapter 3, we'll understand these things in parentheses, but again, the concept is simple. For every 2 aluminums, we must have 3 of these guys.
So it's always 3?
For aluminum sulfate, it is.
But for the
Only for aluminum sulfate.
So how do you know?
Well, you wait till chapter 3.
Oh.
And you'll this is just something to look forward to, isn't it? We have cadmium, copper, and zinc, and here are their densities. A metal with a volume of 15 and a mass of 133. What is the metal? All you have to do here is do what? Just calculate a density, right? There's lots of words in the question, but all you have to do is calculate a density. We have a mass of 133. We have a volume of 15. If you do the division, it's simply 8.92, which matches with copper. A balloon contains helium. This is its density. If the mass of the helium in the balloon is 2.225 grams, what's the volume of the balloon in liters? Well, we're given here units of cubic centimeter, aren't we? Probably the simplest thing. We're dealing here with a mass, and we know a density. We're looking for volume, right? Density is mass divided by volume. Take that equation and solve it.
1.15.
Just take it and solve it for volume. Plug in your numbers, and you'll get 12.5 liters. Now actually, because we're using cubic centimeters here, we get 12,500 cubic centimeters. But remember, the question says volume in liters. Wouldn't you hate yourself if you did the calculation right and you just didn't read the problem? Don't let that happen. 12.5 liters. And finally, this guy is a little bit amazing, actually. Seawater. We are all familiar with seawater having salt and water in solution. Well, it also contains a lot of magnesium. In fact, magnesium in seawater typically is about 1.41 grams of magnesium per kilogram. Now, kilogram of water is, a good sized water bottle, something like this. And there's still 1.41 grams of magnesium in it. That's a lot. What we want to do here is to figure out what mass of magnesium there is in 16.5 liters of water. Well, we are given a density. We are given a number of liters. We could set up our algorithm here and figure out how many grams of water we have, and therefore how many kilograms we have. If we know how many kilograms we have, just multiply that by 1.41, and you should actually get 24. If we have 16.5 liters and the density is 1.03 grams per cubic centimeters, that should come out in your calculation to about 17 kilograms. If you didn't try it or didn't get it, check it, make sure you get it. Once we know the number of kilograms, multiply it by 1.41, and you get 24 grams of magnesium. Now, right now, you should be sitting back and saying to yourself, in your entrepreneurial voice, my goodness, there's a lot of magnesium in there. What can I use magnesium for? Well, a lot of it is recovered from seawater, and it's actually used a lot. So somebody else thought of that, but it's a very good question.
Can
There's
you show
lots.
us the steps how you get to this? Because I don't get it.
Okay, well, let's see if I can actually use the chalkboard still. Let's see, we have a density of 1.03 grams per cubic centimeter. Right? That's a ratio. We have a given here of 16.5 liters. Let's put it up here. Now, we must convert our liters into cubic centimeters, right? We can do that because we know that every liter is 1,000 cubic centimeters. So we could put another ratio in here. We could say there are 1,000 cubic centimeters in 1 liter. Now, just like magic, our liters will cancel, our cubic centimeters will cancel, and we just take 16.5, multiply it by 1.03, and totally doing it in my head, not looking at the answer at all, 17 grams. Once you know how many grams, or, I'm sorry, it's kilograms, right? Once you know how many kilograms you have, just take our 17, multiply it by 1.41, right? And you get 24. Now, there's no tutorial that does these types. Oh, wait, here's one more. Okay. Okay, yeah, here's just, this is a simple one. I didn't know this one was here. Volume of a sample of magnesium weighs 5.68 grams and has a volume of 3.36. So based on this, we can calculate, this is mass, here's a volume, we can calculate a density, correct? Now this is a floating question. We know that whatever has the lowest density is going to float. So once we figure out what the density is, and that'll be 5.68 divided by 3.36, we're going to compare it with the density of chloroform, carbon tet, and dibromomethane. If the density we calculate is less, it will float. If it's more, it will sink. Turns out that dibromomethane is the only one on which it will float. If we divide 5.68 by 3.36, we get 1.69. The density here is less, that's less, but this is more. So just like our cannonball floated on mercury, our lump of magnesium will float on dibromomethane. And now I think we are finally done. Thus endeth chapter 2. And on Friday,